In section 7.1, we're going to be looking at some more identities with trigonometric functions. So we'll call section 7.1 Fundamental Identities. So one thing I just wanted to start off talking about are even and odd. So if you recall, when we were talking about symmetries, we said a function could have it could be even, which means it's symmetric to the y-axis, or a function could be odd, meaning it's symmetric to the origin. And then hopefully you remember what these tests were. A function is even if when you plug in the opposite of x into f of x, you wind up with f of x. It's the same thing. So this was an example where, let's say, f of x is equal to x squared. Well, f of negative x would be negative x to the second, or f of negative x is just x squared. It's exactly the same thing. That's what happens with even functions. Now an odd function, if you were to plug in the opposite of x, you would get the opposite of the function. So for an example, we looked at f of x is equal to x cubed. Now if you were to plug in the opposite of x, negative x times negative x times negative x gives you the opposite of x to the third. And that would be an easy example of an odd function. So let's take those understandings and let's look at the graphs of our trig functions. Just looking at the graphs, just before we move on, you could see that they're symmetries, right? So this one is clearly x squared is clearly symmetric to the y-axis. X to the third is symmetric to the origin. If you take any of these points and reflect them over the origin, you get a point on the other graph. It's a little bit harder to see odd functions, but hopefully you understand that. That point goes here, maybe this point goes here. We've talked about that before. So let's look at the graphs of our trig functions. Y is equal to the sine of theta. Looked like this. Y is equal to the cosine of theta. Looked like this. Y is equal to the tangent of theta. Looked like this. Y is equal to cosecant of theta. Looked like this. Y is equal to the secant of theta. Looked like this. And y is equal to the cotangent of theta. Looked like this. Something like that. All right, so now let's talk about the symmetries of those graphs. Well, sine is clearly an odd function. Maybe I'll show you in a different color here. Any point here, it's not symmetric to the y-axis because there's no point there. But if we do fold it over the origin, there is a point on the other side. So sine is odd, which means that the sine of negative theta is equal to the opposite of the sine of theta. Let's take a look at cosecant. Take this point, fold it over the origin, it's right there. So cosecant is also odd. meaning cosecant of negative theta would equal the opposite of cosecant of theta. We're going to use these when we are simplifying trig functions. It looks like cosine is even because it has symmetry about the y-axis, which means that the cosine of negative theta is equal to the cosine of theta. Similarly with secant, this is also an even function, meaning that secant of negative theta is equal to the secant of theta. And tangent, looks like this is an odd function because it's a cubic graph. And that means that the tangent of negative theta is equal to the opposite of the tangent of theta. And cotangent is a little bit like tricky if you just look at it. But cotangent, if you take any of these points and you fold it over the origin, it does have a corresponding point on the other side. So cotangent is odd. So the cotangent of negative theta is equal to the opposite of the cotangent of theta. Those are some properties using symmetries. Let's move to our reciprocal properties, which we've talked about in another section, but we just want to have some of our properties in the same place here. So just quickly, the reciprocal property said that if you know what sine is, you could take 1 over the cosecant, and that would equal sine. If you go the other way, 1 over the sine of theta would give you what cosecant is. Cosine of theta is equal to 1 over secant of theta, and therefore secant of theta is equal to 1 over the cosine of theta. Tangent of theta is equal to 1 over the cotangent of theta, and cotangent of theta is equal to 1 over the tangent of theta. And one property we haven't talked about yet is called the quotient property. So we have symmetries, we have the reciprocal, we have the quotient properties. So if you remember when we were talking about quadrantal angles, we said if we have a quadrantal angle, y is the sine, x is the cosine, and y over x is the tangent, right? Well, y was just sine, so we could actually substitute that in there. X is cosine, so we could substitute that in there, which brings me to my favorite tattoo. I have a tattoo on my arm that I especially like during the summertime that just says sine of theta over the cosine of theta. And you might be asking, why am I talking about my tattoos in a college class? Is that appropriate? Well, because I have that on my arm, it's right below my wrist. So I can't draw, so forgive me. Here's my hand. It's really terrible, but that's where my tattoo is. It's right on my wrist there. Especially during the summertime, I could say that I have a tan arm. That's a bad math joke, right? But sine over cosine is tangent. The reciprocal would be cotangent, which would be cosine of theta over the sine of theta. So please make sure you remember those quotient properties. And while we're here, we might as well mention our Pythagorean identities. If you remember when we had our triangle here, we said x squared plus y squared equals 1 squared, right? And y was sine, so sine squared plus cosine squared would equal 1. If we divided everything by sine, sine over sine is 1, cosine squared over sine squared you could see now is cotangent squared. and 1 over sine squared is cosecant squared. Those properties we get by dividing by sine squared. And then if we divide everything here by cosine squared, we get tangent squared plus 1 is equal to secant squared. Really what I do, if you were to stop me in the hall or off campus and you say, hey, Professor Ottino, quickly, 1 plus tangent squared, what is it? I'm not going to know, I'll be honest with you. I remember this property, and then what I could always do is just divide by sine squared and cosine squared to get the other two. So I'd recommend just as long as you can remember sine squared plus cosine squared is 1. So let's practice using some of these properties. So I'll say given tangent of theta is equal to negative 5/3, and we are in quadrant 2. Let's find, so quadrant 2 puts us right here. Remember what's positive in quadrant 2? All students take calculus. Sine is positive in quadrant 2. Everything else is negative besides cosecant. Alright, so given tangent is negative 5/3 in quadrant 2, opposite over adjacent. Well, 3 would have to be negative, 5 is positive. Let's find secant of theta. Well, we could look at our triangle, and using Pythagorean theorem, negative 3 squared plus 5 squared would equal our hypotenuse squared. 9 plus 25 is 34. So our hypotenuse is equal to the square root of 34. The secant would be the hypotenuse over the adjacent side. So it's negative root 34 over 3. But the idea with these is let's practice using our properties. So I could see in the properties that tan squared plus 1 is equal to secant squared. Well, if I know tangent is negative 5/3, I'm just going to practice using a property, and let's see if we get the same answer we just talked about. We should get negative root 34 over 3. This would turn into 25 over 9 plus 1. 25 over 9 plus 9 over 9 is 34 over 9. Taking the square root, we get the absolute value of secant is equal to root 34 over 3. But we are in quadrant 2, so secant would be negative. So secant of theta has to be negative root 34 over 3, which is the same answer we would have got using our triangle, but you could see how the property works as well. What about if I asked you to find the sine of theta? Okay, well, we know what tangent is, and tangent we could easily convert to cotangent. So do we have any property, I'll zoom up a little bit here, scroll up, that uses tangent or cotangent and sine or cosecant? That property right there. So we could use 1 plus the cotangent squared of theta is equal to the cosecant squared of theta. Let's plug in. Now if we want to know what sine is, just look at your triangle. It would be 5 over root 34. So the answer would really be 5 root 34 over 34. All right, just like we knew with secant, secant would have been root 34 over negative 3. But that's using the triangle. The idea with this is let's practice using the property just to make sure it all works. So if the tangent is negative 5/3, cotangent would be 3 over negative 5. 3 over negative 5 squared is 9 over 25. 25 over 25 plus 9 over 25 is 34 over 25. when we take the square root of this fraction, we get the absolute value of the cosecant of theta, which would equal root 34 over 5. And because we're in quadrant 2, sine and cosecant are positive, so we get that the cosecant of theta would equal positive root 34 over 5. But the question did ask for sine. So if we know what cosecant is using a reciprocal property, sine of theta would be 5 over root 34, and rationalizing would give us sine of theta equal to 5 root 34 over 34. Exactly what we were expecting. Last one I wanted to talk about is this one. This one's a little bit different. What if I asked you to find the cotangent of negative theta? Well, that's a little bit different. When you have a negative theta, what does the graph of cotangent look like? Cotangent is odd, right? Some people say I'm a little bit odd, especially my high school students. They have no problem telling me that. But the cotangent is an odd function. So cotangent of negative theta, really using the symmetry of the graph, it has odd symmetry, which means if you plug in negative theta, you would actually just get the cotangent of theta. So if we know that tangent is negative 5/3, then the cotangent of negative theta (3 over negative 5). Right? That would be the cotangent of theta, and that's what our answer would be. If it was even, right? So because it's odd, when we put in the opposite of theta, we actually get the opposite of the function. So if tangent of theta is negative 5/3, the cotangent of the opposite of theta would be the opposite of this. So that actually gives us a final answer of positive 3/5. It's a little bit tricky. Bottom line is because it's odd symmetry, cotangent of negative theta is the opposite of whatever the cotangent is. If we know tangent is negative 5/3, cotangent of theta would be negative 3/5. But the cotangent of the opposite of theta would be the opposite of the cotangent. That's where that came from. So hopefully you understand that, and we get the same answer. Just working off of this, I'm not 100% satisfied with my answer there, so let's maybe do a couple more just to make sure we understand. What about if I asked you, let's say, if sine of theta is equal to, let's say, 3/5, and we're in quadrant 1, let's find the cosecant of the opposite of theta. Well, cosecant, if you remember the graph of cosecant, it looked like this. Cosecant was an odd function. So the cosecant of negative theta would be the opposite of the cosecant of theta. So if sine is 3/5, cosecant of theta is 5/3, and then cosecant of negative theta would be the opposite of the cosecant of theta. That would be our answer. We'll do one more. What if I told you if cosine of theta was equal to 4/5, and we're in quadrant 1, find secant of theta, secant of negative theta. Okay, well, think about what the graph of secant looks like. Secant looked like this. That's an even graph. So secant of the opposite of theta is just equal to regular secant of theta. Well, if cosine of theta is 4/5, just regular secant theta would be 5/4. That's how we could use even and odd functions. Let's move on to a new type of example. What if I asked you to write cosine of x in terms of tangent of x? Okay, so let's look back at our properties and see if we have any property that has cosine or secant and tangent and cotangent. Okay, well, I have tangent right here, and I have secant, which I could easily convert to cosine, so I'm going to use that property. If tangent squared of theta plus 1 is equal to the secant squared of theta, I think we wanted to use x, so just to make sure everything's good, we'll put x here. Let's try to get cosine in terms of tangent. So we already have tangent. Let's get a cosine. And now we want to try to solve for cosine, right? So let's just cross multiply. We don't have to make this a super difficult thing. I'm going to multiply here. 1 times 1 is equal to the cosine squared of x times tangent squared of x plus 1. Okay, well, remember we want to get cosine by itself, so let's divide by tangent squared of x plus 1. These would cancel. And we get cosine squared of x is equal to 1 over tangent squared of x plus 1. All right, when we go to take the square root here, we take the square root of a fraction, top and bottom, which turns this into absolute value. Square root of 1 is 1. You're not allowed to distribute a square root like this. You can't just take the square root of tangent and the square root of 1. That's not how square roots work. Like, what if I asked you what's the square root of 3 plus 1? The answer is 2, right? Square root of 4 is 2. That's not the same thing as the square root of 3 plus the square root of 1. So please don't do that. You can only break up a square root if you're multiplying or dividing on the inside. So we do still have this radical in the denominator, which isn't good. So I'm going to actually multiply the top and bottom by the denominator. I'll show you what that does. We can get rid of the absolute value here. We'll just write cosine of x is equal to plus or minus square root of tangent squared of x plus 1. That was our numerator. And on the bottom, we have the square root of the tangent squared of x plus 1 times itself. So the square root and the squared cancel out. It's just like what happens when we have 1 over the square root of 2. You'd rationalize by multiplying by the same root over itself, right? You'd have the square root of 2 squared and these cancel. It's the same idea, we're just using trig functions. So our final answer would just be the cosine of x is equal to plus or minus the square root of tangent squared of x plus 1 over tangent squared of x plus 1. That's how you do it. Okay, so to finish up this section, it's a little bit of an introduction to what's coming up. The next section is my absolute favorite in all of the math classes I've ever taken or taught. I really enjoy this next section. But to get there, let me give you a little appetizer. Let's simplify sine of x over the tangent of x. And when we simplify, we could do one of two different things. We can convert to sines and cosines, which is, I think, what most of you are going to find the easiest. Second thing we could use is use an identity. Sometimes using an identity is faster, but it requires a little bit more thought. You could always get the answer converting to sines and cosines, but sometimes the algebra is a little intense. So let's take a look at this problem. So what is sine over tangent? Well, this is really just sine of x divided by tangent, which is sine over cosine. Now, when you're dividing by a fraction, that's the same thing as multiplying by the reciprocal. And you could see here that the sines would cancel, leaving us just with cosine of x. It's a pretty cool thing. Let's try something else. What if we had the cosecant of x times the cosine of x times the tangent of x? All right, well, let's convert to sines and cosines. Cosecant of x is 1 over the sine of x times cosines already in sine or cosine. Tangent is sine of x over cosine of x. Should have the reciprocal identities, the quotient identities, and sine squared plus cosine squared equals 1. Those should be memorized. Those should be known. You shouldn't have any kind of delay in recalling those. Well, we're multiplying by cosine and dividing. And then we're just left with sine of x over sine of x, which also cancels, giving us 1. You don't get 0, right? Remember, like 2 over 2 is 1. If you have the same thing that cancels on top and bottom, you do get 1. And we'll finish with a grand finale here. 1 plus cotangent squared of theta over 1 minus the cosecant squared of theta. So I'm going to show you two different ways to do this. First way, let's use our identities. Now, if you think about your Pythagorean identities, what is 1 plus cotangent squared? Let's kind of sneak back to our identities. And we had them right here. 1 plus cotangent squared is cosecant squared. And we have 1 minus cosecant squared. Well, so if we know 1 plus cotangent squared is cosecant squared, I'm just going to replace that in the numerator. What's 1 minus cosecant squared? So I'll bring this over and bring this over. So if we just rearrange that formula, 1 minus cosecant squared of theta is equal to negative cotangent squared of theta. Okay, well now we could use our quotient properties. Quotient properties and our reciprocal identities. So this is just the cosecant squared of theta divided by negative cotangent squared of theta. Cosecant squared is 1 over sine squared of theta. And we are going to be dividing by cotangent squared, negative cotangent squared, which is cosine squared of theta over sine squared of theta. When we divide by a fraction, that's the same thing as multiplying by its reciprocal. Sine squareds cancel, and we're left with 1 over negative cosine squared of theta. That's a reciprocal identity for just negative secant squared of theta. So don't get intimidated by this. I know that's a lot, especially the first time you're seeing it, but you don't have to do it this way. This is using the identities, Pythagorean identities. Let me show you how we could just use it or do this with sines and cosines. We should get the same answer. So using sines and cosines, the numerator is 1 plus cosine squared of theta over sine squared of theta. The denominator is 1 minus 1 over sine squared of theta. So we convert it to sines and cosines. Well, we have fractions on top and bottom, so we are going to have to get a common denominator. Common denominator in the numerator is sine squared, so I'll multiply the 1 by sine squared of theta over sine squared of theta. I'll do the same thing in the denominator. I'll multiply the 1 by sine squared of theta over sine squared of theta. So what we get is the top, sine squared of theta plus cosine squared of theta over sine squared of theta. That's the numerator with a common denominator and combined, divided by our denominator, which would be sine squared of theta minus 1 over sine squared of theta. Okay. What is sine squared plus cosine squared? That's a Pythagorean identity for just 1, right? So we have 1 over sine squared of theta times sine squared of theta over sine squared of theta minus 1. These cancel. We get 1 over sine squared of theta minus 1. Okay, so let's try to think about properties with sine squared and 1 in it. I know that sine squared of theta plus cosine squared of theta is 1. So what's sine squared of theta minus 1? We just have to rearrange our property. That's negative cosine squared of theta, and you can see where this is going. 1 over cosine squared is secant squared of theta. All right, so those are some fundamental identities with trig functions. I'm really excited for this next section. Stay tuned.